Hello everyone. Today I'm here with some guest students who did research on the Pictet Spengler reaction. Why am I not presenting today? Oh, I just didn't feel like it. Ah man, the Pictet Spengler reaction. I remember when it was first founded by Pictet and Spengler. I had lunch with them a couple of times and we were great friends. Ah, those were the good old days. Anyways, let's move on. All right, come on now, turn on your cameras, unmute, come on, introduce yourselves.
Hello, I'm Shri.
Hi, I'm Isra.
Hi, I'm Michelle.
All right, good. Now that the introductions are over, let me share my screen. Now let's start with the introduction slide.
In this video, we will be talking about the Pictet-Spengler reaction, which was founded in 1911 by Ahmed Pictet and Theodore Spengler. This reaction is used to create alkaloids in drugs like morphine, quinine, strychnine, and cocaine. The Pictet-Spengler is a special case of the manic reaction. And this reaction is also used in biosynthesis. The products of the Pictet-Spengler can be isolated from products that were initially from nature, like soy sauce and ketchup. Next slide.
The compounds involved include either an aldehyde or a ketone, as well as a beta-aryl ethylamine, and that's just an amine bonded to the beta carbon that's hanging off of a benzene. The amine in the reactant could be either primary or secondary. So you see in our example, we have a primary amine with 2 hydrogens, and in our product, we have 1 hydrogen bonded to the nitrogen. If there were an R group bonded to the original amine, like you would see in a secondary amine, you would see it bonded to the nitrogen in the final product as well. You cannot have a tertiary nitrogen since there will be a deprotonation step in the mechanism, which we'll be getting to later. On the benzene, having an electron donating group on the carbon, either meta or para to the ethyl, would result in higher yields than just a plain benzene. Note that if we put the electron donating group on the ortho carbon, it wouldn't move around the double bond. Anyway, the final product that we see here is what's known as heterocyclic, which just means it has at least 2 different atoms in a cyclic formation. Here, the 2 different atoms are carbon and nitrogen. As mentioned earlier, the point of this reaction is to create a cyclic nitrogen compound. Next slide.
Good job.
The reaction must occur at a slightly acidic pH, around a pH of 6, and a moderate temperature in order to prevent aldol formation. In addition, an aldol reaction is less likely to happen if only small amounts of aldehydes or ketones are used. An amine is absolutely necessary for this reaction to occur. The resonance stabilized positive charge on the amine makes the amine an excellent electrophile. The specific reactant used matters a lot in terms of the yield in the product. Indoles or perols are the best reactants to use for this reaction to give products in a high yield with mild conditions in the lab. As mentioned earlier by Isra, the presence of an electron donating group in either a secondary or primary amine also ensures a good yield of products. Less nucleophilic rings, such as phenols, give a poor yield in products and require a higher temperature and strong acid for the reaction to occur in the lab. Next slide.
All right, well, instead of going to the next slide, let me go to our good old friend Oscar. Here. All right, as mentioned by my fellow students, this reaction is a special case of the manic reaction. Let's see what makes it so special. Here I have a simple acetone under acidic conditions. Note, it's under mildly acidic, like Shri said. Here, what are we going to do with an acetone in acidic conditions? Well, we're going to pronate our carbonyl oxygen, of course. So here I'm going to draw the arrows, and now I'm just going to use Wolfie follows the arrows. And now we have a pronated carbonyl oxygen. Now, what are we going to attack with? The aryl ethylamine that we mentioned in the slides. So here I'm just going to draw it out, get a little benzene ring up in here. Oh man, Oscar's not cooperating today. So here we're going to draw an hydroxyl group, and it's going to be meta to the amine group. And the amine group is going to be beta to the benzene ring. Now let's draw our arrows. We're going to have our nucleophilic amine group attack our very electrophilic carbonyl carbon. Now let's have Oscar draw it out for us. Now we have our nice nitrogen with a positive charge. Now, how are we going to go about this? Well, you could depronate the nitrogen with water, or a little shortcut here, we'll just depronate with the hydroxyl group. So let's do this and this, draw the arrows. See, Wolfie follows the arrows. And there we go. Let me redraw this. Alrighty, now we have a great leaving group. Now, what's one of the most important things that we do in the Mannich reaction? Ah, yes, we form an iminium ion. And how do we do that? We move down the lone pair on the nitrogen to kick off the water. Now let's have Oscar do his magic. And now here we have our iminium ion. Now, what is so striking about this compound right now is we can have a ring formed. Now, how are we going to do that? Well, as our good old friend Andy says, resonance is the answer to everything. And it's a good thing we have an electron donating group to where we can delocalize our electrons. So here we're going to move the double bond. And now this double bond has nowhere else to go, or else we just go around the ring. And since we have a nice electrophile here, we're able to attack it with the double bond. Now let's see if Oscar is going to be able to draw this. He's thinking. Oh wait, he's not thinking. He says, oh, my arrow's too far. Dang it. Let's draw it closer, see if it works. There we go. Don't mind the warning. There is no, wait. Oh man, I messed this up. Forgot my one arrow. Let's redraw this. All right, now we got the thing we want. Now we have our heterocyclic ring attached to our benzene ring. Well, it's not really benzene right now. So how are we gonna, this is a very unstable ring. We have a cation right here. So what we're going to do is we're going to reform the benzene ring. And we're gonna do that by depronating a hydrogen. And we're just gonna go about the arrows just like that. Nice little wave of red arrows. And let's just do our final step here. And now we have our compound. Notice how the substituents on the ketone end up next to the nitrogen in the heterocyclic compound in between the nitrogen and the benzene ring. Also note how the hydrogen here remains and is left untouched. Now, this is why primary amines and secondary amines work in this reaction. However, tertiary amines don't work here because you need a hydrogen to use for depronation and elimination. Let's go back to the slides. Here we have the mechanism all drawn out, looking pretty. And here I have an acronym as Professor Druckhammer used to use in 331 with PADED. Here we have PAD-PED. I know. Get your giggles out now, everyone. I get it. So P stands for pronation of the carbonyl oxygen. Attack is the attack of the nucleophilic amine group of the aryl ethylamine. Depronation is for D, when we depronate the nitrogen. And P is for pronation of the oxygen. We did this in a shortcut step, but the acronym works better this way. So now we have an elimination step for E with the iminium ion formation, attack with the double bond for A, and depronation of the hydrogen in between the rings to get our final product. Now, moving on to the next slide.
All right, so here we have a practice problem. Pause the video. Lawher knows you didn't, but whatever. Okay, so what are we looking for? We want the cyclic ring of the ketone reactant to be a part of the substituents on the carbon alpha to the nitrogen in the final product. And then in the amine reactant, we see an R group attached to the nitrogen, which should still be attached in the final product as well. We can eliminate E right away because that's cocaine. I don't know how that got there, but moving on.
The aryl ethylamine has to stay conserved in the reaction. Choice B is wrong because the aryl ethylamine is not conserved in that product. So we already eliminated one choice. It is conserved in A, C, and D. A is wrong because it doesn't form the ring off of a singular carbon. C has the correct structure, but instead of forming the ring off of the carbon next to the nitrogen, you have a bond attached to the ketone, which makes alcohol, which makes that incorrect. So we know our answer is D. Next slide.
There are alternate reactions in forming isoquinoline, a heterocyclic aromatic organic compound. For example, the Bischler-Naprowski reaction uses an amide instead of a primary amine. In addition, it is an intramolecular electrophilic aromatic substitution. In this reaction, we do not need to introduce an aldehyde or a ketone, which is different from the Pictet-Spengler. In addition, the Pictet-Spengler does not form a double bond next to the nitrogen. It maintains aromaticity and uses less carbon in synthesis, which is crucial when you're under carbon count. Next slide.
And this is the end of the presentation. What? What is this? My students have vandalized my slides. Ah, I knew I should have just done the slides myself. You guys got me this time.
7:59 a.m.
Okay, setting up Oscar. Okay. How am I gonna ruin these kids' lives today? Well, they're only just waking up. I need to wake them up. I need to give them some hard problems. All right, I have a good one in mind. Perfect. Good morning, Israel.
Good morning. How are you?
Good. Okay. Oh, it's 8 a.m. It's time to start lecture, everyone. Oh man, we only have a couple of students. Oh, that's okay. All right. So here we have a ketone. Here we have our arylethylamine, and we have our moderately acidic conditions. And now I have some choices for you guys. I'll give you guys 5 minutes about to work out this problem.
5 minutes later.
Okay, well, I hate to break it to you guys, it's not B. So what does that have to be?
B.
A.
A.
A, yeah, A, there we go. Great.